What's up guys, welcome to Simplifysics. In this video I'm going to be teaching you a fast and accurate way of drawing ray diagrams. So here's your notebook paper. Take a scale and pen and choose any line to trace the principal axis. Next, take the scale and pen again and draw the symbol for a convex lens. Remember, your lens must be 3 lines above the principal axis and 3 lines below the principal axis. Then take the scale and pen again and mark a point such that the width of the scale is equal to the distance between the lens and this point. Repeat the same procedure to mark another point, and then label these points as F1 and 2F1. Repeat the same procedure for the other side of the lens. We will now draw the object. So take the scale and pen again and draw an object that is exactly 2 lines tall. Label the object AB such that B is on the principal axis. Now we will first use 2 rays from A to make the image of A. So one of these rays goes parallel to the principal axis. So we will draw this ray. This ray passes through the other focus, and then we will draw another ray from A that passes through the optical center O. So where both of these rays meet is the image of A, that is A dash. The image of B will be on the principal axis, so here's our image. So as you would have already noticed, the object was beyond 2F1, and we will now describe the image. So to describe the image, we need to consider its location, its orientation, its size, and its type. So I use the acronym LOST. L for location, O for orientation, S for size, and T for type. So in this case, the image is located between F2 and 2F2, and its orientation is inverted. The size is diminished because while the object is 2 lines tall, the image is not 2 lines tall. The type is real because the rays of light actually meet to form the image. So we will now consider several cases where the object is located at several different locations. So let's consider an object which is at infinity. Parallel rays of light will meet at F, and the image is inverted, highly diminished, and real. If the object is located beyond 2F, as we have already seen, location is between F and 2F, it's inverted, diminished, and real. And if the object is located at a distance that is twice the focal length, the image formed is at 2F, it's inverted, it's of the same size, and it's real. So we bring the object closer and we find that the image this time is beyond 2F, it's inverted, magnified, and real. When we keep the object at F, the rays of light are so parallel that the image is at infinity, inverted, highly magnified, and real. We bring the object still closer such that it is between F and O. So now you can see that these rays are not going to meet, they diverge. So what we do is extend these rays backward and we get an image that is on the same side of the lens. Its orientation is direct, it's magnified, and it's virtual because the rays are not actually meeting, they appear to meet. So that's all about image formation by a convex lens. We will now consider a concave lens. So with the concave lens, regardless of wherever you keep the object, the ray parallel to the principal axis diverges, and we can't do anything but extend this ray backward to get an image that is on the same side of the lens, erect, diminished, and virtual. And now the summary of this video. A convex lens forms real images when the object is placed beyond the principal focus. As the object is brought nearer to a convex lens, the size of its image increases. A convex lens forms a virtual, erect, and magnified image when the object is placed within its focal length. I haven't discussed the uses of lenses in this video. I'd encourage you to find out the uses, but the use of a convex lens depends upon the location of the object. And finally, a concave lens always forms a virtual, erect, and diminished image. So that's all about image formation by lenses. In the next video, we will be talking about the focal length of a lens.